Okay, so now I'm going to introduce our speaker, Ian Danforth. What's the title I've been talking about? This
Biological Information Processing for Roboticists.
Okay, and cool. So, thank you very much.
Thank you.
Okay.
Everyone mill about for a little bit, as there will be undoubtedly technical issues starting everything, so you know how it is.
Just had to find the plug.
Yellow one. Yep, I got it.
There we go.
Cool. Jing is wonderful, by the way. If you haven't checked out Jing, okay. This is biological information processing for roboticists, which I hope is every single one of you. And I'd like to start with just a little bit of magic. You've all been wondering why there is fruit under your chairs. So those of you who have fruit under your chairs, go ahead and get it now. If you don't have fruit under your chairs, don't worry. The magic tonight will not be performed by me, it will be performed by you. And specifically, it will be performed by people who have fruit and somebody on their left. If you have somebody on your left, please turn to the person on your left and ask them to close their eyes. This is your partner, ask them to close your eyes. If you don't have someone on your left, turn to your person on your right. It doesn't really matter. You just need a partner if you have fruit. Okay.
All right, my eyes are closed.
Okay.
I'm on your left.
Good. The people with fruit, take the fruit and shuffle it in your hands. Make sure they do not know if they are going to be handed an apple or a pear. Do not tell them which of the pieces of fruit you are going to hand them. Now hand them a piece of fruit. Don't let them smell it, taste it, anything like that. Just let them feel it. And now ask them which piece of fruit were they handed. All right, everybody open your eyes. Did anyone get that wrong? Please raise your hands. Almost none of you, maybe one, maybe you aren't willing to admit it. That was amazing. That was magical. If you don't believe that your partner has magical powers, I challenge you to go home and build a robot that can do the same thing. Because as Feynman might have said, what I cannot create, I do not understand, and might as well be magic. Now, I will grant that at Willow Garage, given 2 interns in 2 months, they could probably do this with the ER2, but right now, even the best robots in the world can't do this task. As a side note, to make sure that every single one of you would be able to accomplish this little bit of magic, I went to Safeway and I touched a lot of fruit. And I can tell you that you have the power to distinguish between many types of fruit and even some legumes. But as I said, unfortunately, even our best robots do not have this power. They're not adaptable enough. They have to be programmed for months to attempt this kind of task, and frankly, that's not good enough, because what do we want? Smarter robots. And when do we want them? By 1960. We've been waiting a long time for the promise of intelligent robotics, and frankly, I'm tired of waiting. So I have 2 points to try and bring us into this new age of intelligent robotics that I hope I can convince you of tonight. 1, the key to building intelligent robots is understanding biological intelligence. I don't think this is a terribly controversial idea anymore. There's been massive inspiration throughout the robotics industry on how to make intelligence and how to get robots to do smart things by looking at biology, looking at the physicality of hands and morphology, as well as information processing. But the point that I really want to bring home tonight, and I think this probably will be controversial in this group, is that the key to biological intelligence is touch. It's touch. I know everyone here loves vision, and they love sonar, and they love radar, and they love the Kinect. But I want to convince you that the key to intelligence is touch. And so why touch? Well, the first point is that it came first. Touch, if you look through the history of biology, if you look at all even remotely intelligent species, they have a sense of touch. If you go back to even the simplest organisms, you go to a sponge larva, if you go to C. elegans, even if you go to a bacteria, these all react to mechanical properties in their environment in a seemingly intelligent way. Their behaviors are altered by the mechanical properties and the mechanical forces in their environment. The C. elegans only has 302 neurons, but it does this quite well. The sponge, when it grows up, it doesn't even have a nervous system. Bacteria, obviously no nervous system, but still are able to form biofilms based on whether or not they're attaching to hard surfaces or not. So that's first. Touch is everywhere. It came first. Secondly, it is absolutely essential for survival. If you want to create something that is intelligent, you want to give it a body, you want it to move around in the world and interact in an intelligent way, you want it to be able to survive. And you have to ask yourself, well, let's look at the history of biology. Let's look at all intelligent species and say, well, what's important for the survival of those species? And I'll tell you that touch is absolutely critical. If you ask the question, is hearing important? Well, the National Association for the Deaf reports that there are over 400,000 Americans living with deafness in both ears in America today, living perfectly fine lives. They're intelligent, they grew up, they developed exactly those skills that we wish robots had. What about sight? There are 1.3 million blind people. This is legal blindness. If you look to people who are just visually impaired, the number is closer to 21 million. And these people have a wonderfully vibrant community. Nothing wrong with their intelligence. But what about touch? There are 50 people in the world who do not have a sense of touch. And this is a rough estimate because obviously such small numbers are hard to measure. But congenital analgesia type 2 has a ridiculously high mortality rate, over 80% by the age of 25, and it's extraordinarily rare. So if you get it, and that's very, very unlikely because biology has selected against that, you're very, very likely to die. Touch is absolutely critical for survival. Point number 3, touch is amazingly powerful. There are so many tasks that you want your robots to do, that I want my robot to do. And we think, oh, well, we need to be able to see the objects. We need to be able to hear other people around us. We need to be able to communicate. But think about what you just did. You did something that no robot could do. You correctly identified 2 objects, which are very similar, and you differentiated them easily because you have all of these powers granted to you by the sense of touch. Some of these are proprioceptive, some of these are mechanoreceptors, some of these are granted by free nerve endings. But you have all of these wonderful abilities to sense damage, slip, vibration, hardness, temperature, etc., all through the sense of touch. And finally, the last point I want to make about why we should be looking at touch before everything else is that it is relatively simple and well understood. Vision is massively complex. Massively complex. Millions of photoreceptors in the eye. Huge percentage of the cortex devoted to this task. Whereas if you look at simple organisms that have a sense of touch, that do intelligent things, you can understand them in a very, very detailed way. This is Aplysia. This is a California sea hare. It's a slug. It has a very simple nervous system. This is not a slug. This is Eric Kandel. He's a professor of neurobiology at Columbia University. He has a massively complex nervous system, and he used his nervous system to study that of Aplysia in excruciating detail. He has given us huge amounts of information about what happens when you touch this slug. And for that, he won the Nobel Prize. And this is what he won it for. This system, what happens when you touch one part of one slug repeatedly, how does the behavior change? And underlying that, what are the very, very specific information processing pathways, chemical pathways, etc., that mediate both learning and behavior. So to reiterate, touch is extraordinarily important. It came first. It's essential for survival. It's amazingly powerful. And I actually believe we have hope as individuals of understanding it well enough so that hobbyist robotics can take the lessons of neurobiology, take the lessons that we've learned from studying touch, and apply it at home. So how does touch become intelligence? That's the second really big leap that you have to make, that just with touch that we can become intelligent, or we can do intelligent things. Well, I want to read this sentence because it's quite dense, but it's very important. Many overlapping sensory modalities are processed in a massively parallel, competitive, hierarchical process to produce distributed representations, facilitate learning, and generate predictions about the future. And this is true for all senses, not just touch, but we're going to be focusing on touch tonight. So let's break this down. Many overlapping sensory modalities processed in parallel in a competitive fashion in a hierarchy to produce these distributed representations, which I'll talk about, to produce learning, and eventually to produce predictions. All of these are the key facets of biological information processing that if we learn to imitate and replicate, will produce agents which are as good as biological intelligence. So let's look at many. What is this? What do I mean when I talk about this? Well, these are some famous robot hands. Probably you can identify them. Here we have a Robonaut hand. Here we have a hand from, or a gripper from PR2. And down in the corner we have 21 from Waneda University in Japan. 3 extremely expensive pieces of machinery. Very powerful, very advanced sensory organs. Robonaut unfortunately only has 33 sensors. PR2 has 22 tactile sensor elements in its 2 fingers. I don't actually know if that's in either one or in both. And 21 has 4 6-axis, 4 sensors in each one of its fingertips. It only has 4 fingers, as well as distributed sensors in its palm. But what about biology? Humans have 17,000 mechanoreceptors in your palm alone. That's in each hand. There are so many more receptors when we are talking about touch, when we're talking about vision or hearing in biological systems, that it is no wonder that we have such trouble dealing with the world in our robots. We are handicapping ourselves, we are putting blinders on ourselves because we simply do not get enough information to start processing, let alone make any intelligent decisions based on it. The second point, overlapping sensory modalities. Here's an unfortunately broken view, close-up view of a PR2 gripper. As you can see, the sensors are arrayed in a regular grid pattern. There's some on the top, there's some on the sides. This is very non-biological. In biology, you have huge variation in sensors that all overlap in exactly the same place. These are some of the names of the sensory organs that you have in your hand that exist, thousands in every single one of your hands, especially in your fingertips. This is what they do. Each one is designed to specifically capture a piece of the entire picture. So, for example, when you picked up the apple or picked up the pear, each one of these sensory organs was capturing a different view of the same data. And then what happened is something amazing, something practically miraculous from the perspective of roboticists. We were able to take out all those things that didn't matter, pay attention to only those features that did matter, and distinguish between those features that did matter to determine whether or not we were holding an apple or a pear. Here's what they look like. If you look at the bottom part, this is a single spot, and this is just to illustrate that you have all of these sensory modalities overlapping in a very, very small part of your skin. Some of them exist only in the papillary ridges, your fingerprints, and some of them exist a little bit lower down so that they can cover a wider area and give you interesting abilities like sensing perfectly 250 hertz vibrations, which is what the Pacinian corpuscles do. Now let's talk about parallel. I think everyone is aware of this problem, and not many people are going to actually deal with this problem. Biology deals with parallel processing. Here are the nerves in the arm. It looks like they're converging. It looks like you get into an ulnar nerve, and it looks like you get up into the neck, and things are actually converging. What you don't see that this is cable bundling. It's not convergence. This is cable bundling. All of these sensory signals are happening and moving in parallel all the way until you get to your spinal column. In fact, there is no processing that is done before you get to the spinal column. In fact, there is one axon that travels from your fingertip all the way to your spinal column, and it is only there where you get the first level of processing. And it's all done in very, very small sensory organs and groups of sensory organs. And this travels all the way up to the brain, so that in the brain you can see an exact representation of where you're being touched, because the signal is carried all the way up to the cortex. This is not a problem of dimensionality. This is not dimensionality reduction. In fact, there's dimensionality explosion as you go up the hierarchy and into the brain. And we'll talk about that in a little bit. Now, competitive. This is actually something that most people don't know about, so I'll take some time on this one. Biology has information compete. We have to determine whether or not something is important. There's so much information in the world. Some of it's important and some of it isn't. I'll make the point that biology considers nothing noise, but some of it is important in some contexts and some of it's important in others. This is what's called the Mexican hat phenomenon, or Mexican hat diagram, where you have one piece of sensory information that's very powerful, and it is enhanced, and it tries to suppress all the information around it. It's competing with information around it. So if this is a single point of touch on your finger, it will try and compete against single points of touch around it. This has the property of enhancing contrast. But more importantly, between sensory modalities, between all of those different views of the world, there's actually a competition. If you think about it, if you imagine holding an apple, or if you have an apple in your hand and you run your finger across the top of the apple, you suddenly begin to be aware that there's a curve down toward the stem, where the stem is. And this is an extraordinarily salient piece of information in determining whether or not you have an apple or a pear. That curve of information, which is largely reported by Ruffini endings, suddenly takes over. And this is what's important. This is what you pay attention to, because each one of these sensory modalities is competing as they go in the spinal cord, in the lower processing centers of the brain, and all the way up into the cortex. Hierarchical. I've already mentioned this a couple times. Every piece of information, every point of contact is processed in a hierarchy as it goes up into the brain. Let's take these sensors and see how they might be combined. This is entirely hypothetical, but it does illustrate a couple interesting points. You have a pain sensor, a couple edge sensors, pressure, stretch, etc. And now you get up into the spinal cord. And what happens? Many people think that you throw away a bunch of information and you combine it into maybe larger representations of the world. That's not actually what's going on. You keep all the underlying representations, you keep all the underlying information, and you get this whole new level of views into the world. Because with two edge sensors, you know that it moved from one to the other, and you get this moving edge sensor. With two pressure sensors, you can tell how big something is. With two stretch sensors, you can tell the contour of an object. So now you don't just have those first initial views of the world, you have the first initial views of the world plus a whole new set of views of the world that are made up of smaller views themselves. Let's move up again. Maybe in the lower part of the lower part of the brainstem. The pain sensor comes in. It's taken a shortcut. It's gone all the way around. It's incredibly important. Now we know that we're being cut. We also have a curved object sensor because we know something is large and it's curved. And finally, we have the big old knife sensor. We know that we've been cut, we know exactly its shape, and we know to react to that, running away if it's a mugger, or just pulling our hand back if it's a reflex reaction. This is the process of bringing these distributed representations of the world, the multiple differentiated signals, and combining them into new and interesting views of the world that we can use to pick between what is important and what is not important in the world. Okay, I've used this term a couple times. Yes.
Biological evidence.
Yeah, so probably the easiest way to see this is actually in vision research.
I've seen that going through the before levels of
Yeah.
works. I I haven't, I'm not aware of any touch.
Well, yeah, so,
Same kind of study there,
yes.
same layers as
Well, I mean, they're not exactly the same layers, but they have it's the same hierarchical flow. Yeah, and it's true for all sensory modalities. At least, yeah. I mean, many people don't start counting layers until they get to the cortex. I would argue that processing that happens in the spinal cord would be the first layer. So, yeah, that's about right. On that order of magnitude, certainly. And I've used this term, so let me get to defining what I mean by this. As I talked about, distinguishing objects, the ability to tell whether or not something is important or not important, or close to you or far away from you, or one thing or the other, is an incredibly difficult task. It's incredibly difficult to do in a robust fashion. People have been working on this for decades, and I want to argue that the reason biology is so good at it is because we have these distributed representations. We have all of these sensory signals that we're using all the time that are competing against each other, and only those ones that are actually important or different win out. So as you can see, there's similarity until you get toward the bottom of this hierarchy, and we're actually moving up the hierarchy here. These are more interesting features that require more sensory input until you can absolutely determine just with a sense of touch whether or not you're holding an apple or a pear. And I don't think I can emphasize the value of these distributed representations enough, or how it can change your view of the world, because we're so used to thinking about contact and vision and hearing as a unified action that we're actually feeling one thing. But that happens much, much later in the processing stream. That happens way up at the top of the hierarchy in the cortex. At the base of the processing, the thing that you should be thinking about when building your robots is dividing that information into as many different modalities as possible so that you can identify those few bits of information which are similar if between two apples or between two pears, or those few bits of information that distinguish something that is very, very close together. Next, learning. This is something that I find computer scientists have a difficult time with, this premise that I'm going to suggest. Not that learning is difficult for computer scientists, but that over time, your program should do different things given the same input. If you give your program the same input again and again and again, and it does the same thing, you have made a dumb robot. Because nothing in biology works like this. Here's our sea hare, thank you, again. And this is what learning looks like. This is the most simple, best studied form of learning there is, habituation. If you touch the siphon, these guys live underwater and they breathe in water, etc. If you touch the siphon of a sea hare, it will withdraw its gill. This is called the gill withdrawal reflex. But if you do it again, it will withdraw slightly less. If you do it again, it will do slightly less, etc., etc., etc. It will learn that this brief, light touch is not important. It will learn to ignore it, and it will adapt its behavior. And that is incredibly important. And this is the kind of thing that neurobiology and neuroscience can show you exactly what you should be doing. Yes?
How come there's the jump up in the ground?
So each one of these is a trial that has a resting period between it.
Oh.
So what you're seeing here is short-term and longer-term memory being developed.
Okay, cool.
Yeah. And finally, this is the why. This is the why biology operates like this. This is why these processes have been conserved over 1 billion years. And this is why all intelligent animals and species do this. It's to make predictions about the world. It's about finding out before it happens what is going to occur when you extend your arm. It's about predicting where food is going to be. It's going to be predicting whether or not you are... let me give you a concrete example. As you're sliding your finger across an apple, you're making a prediction. You say, it's going to continue to be smooth. But it's continuing to be smooth doesn't tell you whether or not it's an apple or a pear. It's that moment where that prediction is violated, where it suddenly curves off and becomes a stem. That's interesting. It's being able to compare what you think is going to happen to the reality of what's going to happen that allows you to allows you to react to the world, allows you to differentiate what you thought was going to happen from what actually happened. And here's the great thing for us, for roboticists, reflexes. Reflexes are the first level of intelligence, and they are built in. They are hard-coded into every single one of us and all animals. We don't have to worry about the cortex. We don't have to worry about cortical processing algorithms. We can deal just with reflexes and modifying reflexes through learning, and we can get a huge amount of intelligence just from that. Because, you know, this is a baby, this is the grasp reflex. If you put your finger in a baby's hand, he'll squeeze it. If you stroke the cheek of a baby, he'll turn towards it. That's the moral reflex. All of these are massively important. Here's a giant list of them that I have on my website. And the more that we build these, the more that we understand how to build these and modify them and demonstrate that they can be modified by experience and then demonstrate learning, the closer we're going to get to actually building intelligent machines. So going back, many overlapping sensory modalities are processed in massively parallel, competitive, hierarchical process to produce distributed representations, facilitate learning, and generate predictions about the future. So what are you going to do? What's the takeaway for you guys? Well, I have a couple of small points. I hope you've at least been informed and a little bit entertained. But what I want you to do is explore biology. I want you to recognize that there are 30,000 neuroscientists who show up to the National Neuroscience Conference every year, generating massive amounts of data that you can consume in your robots. What is behavior supposed to look like when it's in an intelligent machine? That information is out there. Find it. If you're in college, take a neuroscience class. If you own a business or run a business or starting a business, hire a neuroscientist or take classes yourself so that you can learn about these kind of things. Build robots that feel. I know it's really hard, it's difficult, it's not vision, it's not all the standard odometry and great things that we know and love, but build robots that feel and write biologically inspired software. Make sure that you're checking against those things that we know are intelligent to see whether or not we're making progress. Yes, I believe that it would be possible for us to completely reinvent intelligence, but why? Why reinvent the wheel when we can study a wheel that already exists? Now, here's some objections that I've heard about this. If you don't understand biology, please ask me. This is what I love. I love reading papers. If I don't know, I will go out and find an answer for you. You can contact me or go to my website, embodiedai.com. If you love playing with vision, awesome. Keep doing it. It's fun. That's what this is about. As long as people are building robots, I'm happy. And finally, this last one is actually a pretty big problem. All those robot hands that I showed you, those are pricey. So I'd like to do something about that, and we'll see whether or not this works. So this is a prototype for an e-textile robotic skin that I'm demoing, or I'm showing off for the first time ever. And this is created by a wonderful woman named Hannah Perna Wilson, a recent graduate of the MIT Media Lab. And the idea here is to produce an inexpensive sensor for us that we can use on our robots to explore the sense of touch in a multifaceted way. As you can see, it's a multi-touch interface. It registers pressure and location. That's good for that one. And let's see if I can show you the other one here. And this is what it's going to look like. It's still being prototyped. These are, it's really funny. She didn't actually have my robotic arm when she was doing this prototype, and so she put all this amazing articulation into the prototype. As you can see, it's got way more degrees of freedom than most servos that you can buy get. So I wish I had servos that could do this, but the idea is to wrap a robotic arm very much like the demo arm from Willow Garage in this sensitive skin. And so that's what I'm doing. I'm going to make that available. The target price point. Sorry.
So was that a conductive fabric then? Or?
Yeah, the fabric is it's actually several layers. It's conductive thread in a crosshatch pattern, so you have rows and columns. In between those rows and columns, there's a piezo-resistive layer, so that when you press down, you actually get additional current flow, and it scans across each of those to do point localization. And the target price point for that is $150. I hope this is affordable, and I can make it available to everyone here. Obviously, I'm paying for this because I want it, but I also want everyone here to get a chance to use it as well.
So, excuse me, how large a sensor area is
That's equivalent to you remember the TurtleBot platform that came up here with the arm? It's meant to cover that arm. Yeah.
What's the resolution?
It's currently, that's TBD. Currently it's an 8x8 matrix is the one that you saw. So probably on the order of several millimeters between points. Yeah. And let's see if I have any points here. The problem with going in and out of these slide decks is it just decides that you really want to go back to the beginning and start all over again. Oh yeah, you can follow along at okay. You can see it all over again, fast forward. It's wonderful. Those from Google, please take notes. Thank you. There you go. You can follow along with this project at lucia.at. That's her website. Yeah. And for people to write that down. And that's it. That's who I am. Thank you all. It's been a pleasure. And I don't know if we have time for questions.
We definitely have time for questions. I have a request first. Could you mail that information to the list? Not on the list yet?
Sure.
Okay, one. And I'd like to request that as you make progress, please send us status reports, because that's been what's killing us in the robot field. We're struggling for sensors. We're still using sensors that that's basically were designed for urinals.
Yep.
So just, there's lots of room to improve. Other questions?
I read the book on intelligence, and that was all about the prediction down, meeting the model up. And the problem is the brain is so massively parallel, and our processes are so narrowly serial that it's, I can't, how can you do 17,000 sensors?
Well, there's one fact that that gives me hope, because that's really hard. It's very difficult to take all of that information and process it in certainly nowhere near as efficient a way. But the fastest reflex in the human body is about 10 milliseconds. That's the blink reflex. The average reflex is about 30 milliseconds. And when you think about having 30 milliseconds of round-trip time when it comes to robotics and standard internet speeds, that's an eternity. The brains of your robot do not have to be in your robot. They can be in the cloud. You can harness the massive explosion of available processing power by offloading all the processing to somewhere else, and you're still going to be in the ballpark of biological timing.
But you have to deal with the bandwidth to get it in and out.
You do have to deal with the bandwidth is the hardest problem, but there's some pretty good compression speeds out there. Yes.
So it seemed like what you were proposing a few slides back almost was begging for a different kind of operating system, or at least a different programming paradigm.
Well, I really like, it can be, I like to put processing at each, build a hierarchy in ROS so that, I subscribe to a topic, do processing, start a new topic, and build it myself, essentially. So I think ROS is perfectly capable and usable for this problem.
Or even with this randomization of the outcome and so on, the learning and the randomization. And
I'm not, it's not randomization. I'm not sure.
the learning aspect.
The learning aspect, yeah. So that's how you need to incorporate memory, right? So at some point you need to remember that you've seen a pattern and react to it in a slightly different way. And even at that, you have to, the processing and memory have to be local, or at least accessible from a local, maintained local.
I've tried to study neurological and scientific data, and it just seems like everything that they publish is just characterization of different areas and different shapes of the pyramid neurons versus. It goes on, and you never really find anything that looks like a circuit that does something. Even in the C. elegans that you spoke about, because it's 390 neurons, they map that out, totally. And yet I still haven't seen any publication that says, okay, well, this works because, signals go from here to here to here to here, and that creates a motor output.
Well, that's what this is. And you can
Is
find...
that, what is that?
We can't hear the question.
Oh, sorry. The question is, neuroscience articles are confusing as heck. Why isn't there something that shows me simply how I go from a sensory input to a motor output? And where is an example of that actually happening in biology? And I think that this is probably the best one that I've found, which is you touch a single sensory neuron on the skin of aplysia. It is connected to a finite and well understood number of motor neurons that are modified by these interneurons that then generate motor output. And an excellent and very accessible book is called In Search of Memory by Eric Kandel. It's a combination of his life history and his work. I would recommend it to anyone. In Search of Memory by Eric Kandel. Anyone else? No? Oh.
What's the bandwidth of the nerve?
It varies depending on the sense. For example, vision is about 10 megabits per second. And that's in each of the...
15,000 sensors on the finger. They each have one channel for the brain, right?
They each have one channel, but they're very different. Like, for example, the Pacinian corpuscles, they have a highest, well, okay, so the maximum response of any neuron is 500 hertz. You can't get faster than that in a neuron. So if you think about saturating the channel, you've got every 2 milliseconds, you've got a signal coming down the channel.
Can we consider this as a binary signal?
It is a binary signal, and it's the coding is done as a frequency code. So you either have a lot of signal or you have a little bit of signal for intensity, and you have off and on for whatever you're processing.
I watched nerve processing when I was in college,
Mm-hmm.
and I noticed that some nerves put out 1 pulse, some put out 2, and some put out 3,
Mm-hmm.
and the pattern of those changes depending upon things. For example, you can pick white light and shine it in your eye with a certain pattern, and you'll see a color,
Mm-hmm.
because that is the pattern that your color receptors actually sense, so your brain knows that that's color. And
I don't think that's true in vision, but there are plenty of, because the cones are very frequency selective. They do have very specific peaks, but if it's white light, I'm sure that if you are targeting if you happen to be targeting, all the green cones with that pattern, you'll see green because they're in a fairly regular, understandable pattern.
well, I'm saying if you just flash white light on that wall
Mm-hmm.
at the right pattern, you can see a color.
Cool.
Huh.
Cool. All right. Thank you.
Thank you very much.
Okay, we're now going into the final phase of our thing. I realized that I forgot to do something. We're supposed to vote in our new members. We have one new member. His name is Ian Danforth.
Hi,
How many
everybody.
people would like him to join our club?
Yeah.
Yay! Okay. So from here, on out until about 10, we just mill around and talk to one another. Thank you very much, and please come to our meeting next month, where we have the 3rd phase of the tabletop challenge. Did I go?
Phase 3, baby.
Okay, thank you very much. Have a good night. I assume it's okay to eat the fruit now, right?
I pulled the print so someone else can
Okay.
eat it.